see if this works. Some thoughts about how we could move towards causal NLP. So let me start with image recognition. So we are all quite intoxicated with the success stories of deep learning. If we have large data sets, we think we can reach human level object recognition, where you can recognize all these cows. However, if we have a cow in the test set, which looks very different, or which is in a very different context, in this case, cows sitting on the beach or in front of the sea, and these systems may not recognize them anymore. And the reason, of course, is that machine learning relies on correlations rather than causality. And if such an object appears in the test set in a context which may even have been negatively correlated with the presence of that object in the training set, then it doesn't recognize the object in the test set. Maybe even worse, we have this phenomenon of adversarial vulnerability, where if we have even just a tiny violation of the usual ID assumptions, or the assumption that the data are independent and identically distributed, so we have a tiny violation by adding a little bit of malicious noise to an image, then suddenly we don't recognize, or we label this little piglet as an airliner, which is quite an absurd mistake. So there's a heavy reliance of present-day machine learning on the IID assumption. And I'm going to argue that this is a shortcoming of machine learning, which should be addressed by trying to learn causal relationships rather than just statistical ones. And of course, this is a causality workshop. I don't have to explain the Reichenbach common cause principle to you. Reichenbach was maybe the first one who understood that there's an intricate link between correlation and causality. We know they're not the same, but there's a non-trivial link, which basically says that if you find two variables to be correlated, or more generally to be statistically dependent, then there must always be a causal explanation for it. And this causal explanation can be chosen such that it screens two variables from each other. And of course, we all know the standard example. So this is the generic case. This variable causes both of them, and conditioned on that, they become independent. Of course, this variable could coincide with one of the two that we found to be statistically dependent. So the standard example, you've all seen this, storks and the babies. So if these two variables, the frequency of storks and the human birth rate, are correlated, which they are in European countries, it could be that the storks bring the babies, could be that the babies attract the storks, or it could be that there's something else, such as economic development, that causally influences both of them. And we need additional assumptions if we want to distinguish between these three cases. Now, as a generalization of the Reichenbach principle, there's this formalism of structural causal models, which is a nice way to think about causality, in the sense that it's nice to connect it to machine learning, because we think we're good at estimating functions, and the functions are crucial elements of these structural causal models. So the idea here is we have a set of observables that form a DAG, and we have arrows that represent direct causation. A DAG is a directed acyclic graph. Each variable is a function of its parents and a noise term, and all noise terms are independent. If we specify distributions over these noise terms, then these imply a joint distribution over all the observables. And this is a particular kind of joint distribution that has certain properties that are called the causal Markov property, or causal Markov condition, certain conditional independence properties. This also, the entailed distribution, together with the graph, is called the graphical model. And what's interesting about this relationship between the graph and that distribution is that this entailed distribution admits what we might call a causal factorization, which means that this distribution can be written as a product of conditionals. Now, that's not surprising, but as a product of conditionals where we only need to condition on the parents for each variable in this graph. So these are much lower dimensional objects than if you had to condition on many, many other variables if the graph is reasonably sparse. So that's a nice factorization. And it's also a meaningful one in the sense that we can think of these conditionals as mechanisms, because each, just like this thing is something like a mechanism. It tells us how a variable depends on its parents and how a variable would change if we intervene on the parents. So these, each of these conditionals corresponds to one of these structural assignments. So this is a physical factorization of the joint distribution that explains how the statistical dependencies in this distribution come about from these causal mechanisms. And we think of this as a causal factorization, not just because it's a product of these terms, but also because we think of these as independent objects in the sense that we can intervene on them separately. So we can change one of them without that affecting the other ones. The other ones would by default remain invariant as we change one of them. And that's because there are physical mechanisms in the world that we can change in a modular fashion. This is an assumption that one can also illustrate with this vision example. Here we have, it's called a Boucher chair. So here we have an object. In fact, it's actually two objects here, which we can discern from this point of view. But if we look through this little hole here, we perceive it as one object. So it's going to look like this, which means perception fails. We see something that isn't there in reality. And perception fails in this case because an assumption which is made by our perceptual system, an independence assumption, is violated. And the independence assumption is that the object which we're looking at and our perceptual process, and we can think of both of them as conditionals, as mechanisms, that the object is like a conditional that doesn't have parents. So it's just a marginal distribution. And then there's the perceptual process, which is the conditional, and that translates the object into our percept. So these two things are normally independent. So they're not tuned to each other. And then perception works. But if they are dependent, if we look through this little hole, which is so very much adjusted to the positional properties of this object, then perception fails. So in general, we make this assumption that there is, the causal generative process is composed of modules that are independent in the sense that they do not contain information about each other, do not influence each other. And we have a toy example just to illustrate how this kind of assumption can help us distinguish cause from effect. It's a kind of a trivial toy example where y is the effect, x the cause, y is simply a function of x. There's not even noise. We assume the function is invertible. So we can go back and forth at our pleasure. But to create an asymmetry, we're going to assume that the input density over x is independent or does not know anything about the function and vice versa. So if that's the case, if you now think about what this function does to the input density, you will notice that the output density will have large probability mass wherever the function was flat, just from the way densities transform. So that means the output density does contain information about the shape of this function, meaning that if we assume independence in the input in terms of for the cause and the mechanism, then we would not have the same independence between the effect distribution and the backward mechanism, so that's an asymmetry, and we've shown that we can actually use this. We can sort of turn this into estimators, and we can use this for causal inference. And just as an aside, this is also related in rather interesting ways to physics and to the second law of thermodynamics. Namely, if we use a different kind of formalization, which is also a formalization as structural causal models, but not a statistical one, rather one in terms of algorithmic complexity, where instead of the functions, the functional assignments that we have in statistical structural causal models, here we have a Turing machine, T, running a program that depends. So this is the program, the noise variable from before is now the encoding of a program, and it uses as an input the values of the parents. So the output of the Turing machine is running there, and then runs and produces this value x. So now we're going to assume that these UJs, the noises, which are now the programs, are jointly independent in the sense of Kolmogorov complexity. So that a joint compression is not shorter than the sum of the original of the individual compressions. So this is now going to be our model. Then it turns out, so for this model, we can derive a nice theory of causal graphical models in terms of algorithmic information instead of statistical one. So this works very much analogously. And if we use that, then we can explain this, the connection to physics. It's just, I'm going to take 2 minutes on this. If you're not interested in physics, you can relax for 2 minutes. Here, we're going to look at this Gedanken experiment, where we have some particles, think of it, some light coming in, which is scattered on an object, and then we look at the scattered photons. So that's exactly what vision is using, right? Vision uses the fact that the photons scattered by objects contain information about the object. So from this, we can now learn something about the object. So we have a cause, we have a scattering process, which is the mechanism. We have an effect, and the effect contains information about the object. That's how vision works. So why does the effect contain information about the object and not the cause? So why does, in other words, why does photography show the past rather than the future? And it turns out that is actually the same thing as our independence assumption. Namely, it's because we will assume that the cause, this incoming beam of light, knows nothing about the object and vice versa. So this is not tuned to the object, but then the outgoing stuff does contain about information about the object. And we can formalize that if we formalize this independence in terms of algorithmic information. Then we can actually prove that in such a system, the entropy, if we formalize it in terms of Kolmogorov complexity, will be a non-decreasing function of the time evolution. So we apply the time evolution, the entropy cannot decrease, or in the generic case, it will probably increase. And that's the thermodynamic error of time, or the second law of thermodynamics. Now, going back to machine learning, if we make this independence assumption, it turns out we get some interesting implications for different kinds of machine learning problems. So 10 years ago, we started thinking about how knowledge of the causal direction of the data generating process might influence the feasibility of machine learning tasks. And we started with the very simplest case, where we would say, let's assume we have two variables, x and y. We always want to use x to predict y. But in one situation, x is causing y, and the other one, y is causing x. Should that make any difference at all? And it turns out it does make a difference if we make an asymmetric assumption about cause and mechanism. So the mechanism of effect given cause, namely the assumption that they're independent, just like before. If we make that assumption, and we always want to learn the mapping from x to y, then if we go in the forward direction, so prediction and causation are aligned, let's call this causal learning, then in that case, this assumption translates into saying that P of x, P of y given x are independent. Now, suppose you want to do semi-supervised learning. Semi-supervised learning means let's get additional data from P of x and try to use this to get a better estimate of P of y given x. But if the two things are independent, then no matter how much data from this you should get, it shouldn't help you. So we would predict that in this case, semi-supervised learning would be impossible. Whereas in the opposite direction, we would actually assume that semi-supervised learning might well be possible, because in the backward direction, just like in this example that I showed you before with the deterministic function, the backward direction, the effects will have a footprint of the backward mechanism or vice versa. So there will be a dependence between those two things. And one can argue in similar ways that for covariate shift problems, it should be the other way around. Covariate shift problems should be easy to handle in the causal direction, but harder to handle in the anti-causal direction. And this turns out to be nicely consistent with empirical results. So at the time we did a meta-analysis on various empirical studies, and this nicely confirmed that these predictions was consistent. So we did get improvements in the anti-causal direction, or whenever it was not a causal problems or anti-causal learning problems, or also for confounded learning problems, we did not see any improvements in previous benchmark studies for causal learning problems. And we also discussed how this relates to assumptions that people have made to justify semi-supervised learning. It turns out all of them make sense from a causal point of view, or even, I would say, make more sense from a causal point of view than previously. Now, more recently, we started looking at this in the context of NLP, together with Zijing Jin, who is at this workshop and who I think will be happy to answer any questions you might have. She's probably sitting in the room right now. Hello, Xi. She knows a lot more about NLP than I do, and we discussed a lot about causality, and we're scratching our heads how to connect the two things. And this was one of the first projects where she painstakingly went through a long list of NLP tasks, thinking about which ones can be thought of as causal learning problems, so where prediction and causation are aligned, which ones can be thought of anti-causal, and which ones fall into neither category, or maybe they fall into one of them depending on how the data exactly were collected. So you can look through this list or discuss with Xi afterwards, but there are meaningful examples in each of these three categories. And then she checked whether the results are consistent with these theoretical predictions. And she has a paper at the EMNLP where you can look at this in much more detail. So I'll just briefly show you here that we basically, if we use MDL as a proxy for the Kolmogorov complexity, then we do get results which are nicely consistent with the theoretical expectation. So these also seem to make sense. And actually, let me see, I think I'm obstructing here the images. And she also looked at problems of domain adaptation. And also in this case, the results did seem to make sense. So please discuss with her if you're interested in more details. Encouraged by this success, we looked also at various other problems, or we started looking at other problems where there could be interesting connections between causality and NLP. So I think there's a whole space open now to try and use that and exploit knowledge about the data generation process, where people often have a lot of prior knowledge in NLP. And it's not just about this assumption of independent causal mechanisms, but she has also done interesting work on logical fallacy detection, causal discovery for text data in various applications. And something that we are very much interested in for the future is the field of causal representation learning. And I'll use the last few minutes to say a bit about that, what I mean by that and why I think that's an interesting problem. So if we go back a bit to the history of our field, if we think of this field as AI, broadly speaking, this is a picture of Herb Simon, one of the fathers of symbolic AI. And the symbolic AI paradigm influenced by games like chess, we are given the symbols. Someone gives us the symbols on which we operate to produce intelligent behavior. And someone even gives us the rules that we apply to generate intelligence. Now, machine learning did away with that, and maybe that was the great thing, that machine learning learned the rules, and machine learning also learned the symbols and representations. Now, I've criticized machine learning since machine learning just looks at correlations or dependencies, and is not robust with respect to violations of the IID assumption. But then if we move to causality, then usually we've thrown out the baby with the bathwater, because then we basically go back to this formalism of causal graphs where someone gives us the variables and we don't learn them from data. So we are in this pre-representation learning stage, or back to the symbolic age, where the variables are given to us. And I think that's something that we should address. So we have classic AI. If you move towards machine learning, we learn representations. If we move towards causal modeling, we learn interventional knowledge, but not the representations. And ideally, we would like to learn both. So we would move towards causal representation learning, and that should give us representations that are not just statistical, but interventional. So these are representations that tell us what will happen to a system if we intervene. These are representations that should be useful for reasoning and planning. In a nutshell, they should be useful for thinking in the sense of acting in an imagined space. So this is due to the Austrian ethologist Konrad Lorenz. That's his definition of thinking. Of course, maybe it's a limited definition from someone who studies animal behavior, but I think it's a very useful one. So this is really the goal that we want to move towards, to learn this kind of representations. And if you want, if you're out of time, you could stop me now, switch off the video and discuss with Z. If you still have a few minutes, I'll just give you a few ideas what we are trying to exploit in doing so. So I've shown you this factorization before, and this is the factorization of the joint distribution in terms of these causal conditionals, or so-called Markov kernels. And I said the factorization is not just a product of these terms, but it's a product of terms which have a certain type of independence, that we can intervene of them independently and the others remain invariant. And if we just take any other factorization, just like, for instance, this one, which you can take for any permutation of the indices, you get one such factorization. This will not have the property that if you change, make an intervention locally in a system, that only one of these guys will change. So here, if you change one mechanism in a system, then in this factorization, usually most, if not all, of these terms will change. And this we can think of as an entangled factorization. And we think that this entangled one should have these invariance properties, and should have this property that if we make a small change to a system, then typically this will only affect one or a few of these terms, and the other ones shall not be affected. And this is it's a hypothesis that maybe one can use to learn about such systems and automatically learn the representations which allow factorizations that have this sparse change property. So this is one idea. There's a number of other and a number of related ideas that we try to apply. We've so far mostly done it in the visual domain. We're starting to think how to do this also for text. For instance, we've built systems that learn representations, and then we also learn modes of intervening on these representations. That, which in this case, this is a training image, this is a training image, and this is an intervened image, which is completely synthetic, which you could think of as a type of a counterfactual image. This is a koala, that's a teddy bear. This looks a bit like a koala teddy bear. So this is one project. We have other projects that connect causality and self-supervised learning, etc. Or we have a project for learning independent mechanisms that can be transferred across problems. So these are examples of trying to do something in this field, causal representation learning, which I think is fascinating, and I expect will have a very interesting future. I am going to skip over this. So this is a paper, just a little ad that will come out at NeurIPS, which is using these independent mechanisms assumptions in the field of nonlinear ICA. So we're not just exploiting the fact that the original signals should be independent, but also that the mechanisms in the generation of the mixture, the forward generation of the mixture, the causal generation of the mixture should be independent. So coming to the conclusions, our goal in all of our work, not just NLP, is to learn world models. We think we should learn world models for two reasons. One is that they are richer than just statistical models. They're interventional. They move us towards thinking in the sense of Bernhard Lorenz. But we also think they are more data efficient because due to their modular structure, their causal structure that's aligned with the mechanisms in the world, it should be possible to pool data for mechanisms across multiple tasks that share mechanisms in the data generation. So they should have components that are reusable and robust. And if you're interested in this general topic, there's this recent opinion paper about the field. And with that, I would like to thank you for your attention. Thank all my co-workers, and say bye-bye and best regards to the beautiful place where you are right now. Thank you very much.